Hello. Right now, what we're going to do is do a nice compare and contrast between line integrals along a path and using the fundamental theorem of line integrals. So if you take a look at this example, what we are really going to do is do line integrals in two different ways to see the benefits of each. So this one says find the work done by F on a particle moving from 110 to 023. Option number one is we can parameterize a path and then use that parameterized path to do the new deal integral, the f dot dr. And option two, because I'm telling you, we can realize that this is a conservative vector field, which means that we can use the fundamental theorem of line integrals with its potential function. So I am going to go through both of those options right now, and that'll be the only example in this video. All right, so option one is let's parameterize a path. So it says find the work done moving on from 110 to 023. I probably should have put in here that this is going to be a straight line path. I did not. That's my bad. So if I want to parameterize a path, I need an x equals, y equals, and z equals that parameterize my path. So x is going to go from 1 back to 0. So I'm going to let x be 1 minus t. Y goes from 1 to 2. So y is going to be 1 plus t because y goes forward. And then z goes from 0 to 3. So z is going to be 0 plus 3t. Okay, the way I parameterize that so fast is I let x equal x sub 0 plus AT, where A is the change from your initial point to your end point. So X went from 1 down to 0, so its change was negative 1. Y went from 1 to 2, so its change was positive 1. And Z went from 0 to 3, it had a change of 3. So that's how I parameterize that path, okay? So there's my parameterized path. And now if I want the work done, I need to do the integral of f dotted with dr. And so let's see. Oh, I need my limits of integration. When you do this straight line path in the manner in which I just did it, it will force your t's to go from 0 to 1, which is always a good thing because zeros and ones are like the easiest numbers to work with in, most cases. So I'm going to let t go from 0 to 1. And now I'm going to rewrite f, which is 2xy, as 2, 1 minus t, 1 plus t. There's 2xy. And then x squared plus z, that looks like x cubed plus z cubed. Wow, that's really messy, isn't it? No, I think that's supposed to be x squared plus z squared. So if you can't read that, I'm calling this x squared plus z squared to make our life easier. So I have 1 minus t squared plus 3t squared. I'm going to run out of room. And then 2yz is 2 times 1 plus t times 3t. So there's f. And now I'm going to dot that with the derivative of the path, which is going to be negative 1, 1, 3. And that's times, not dr, dt. So here's the way of evaluating line integrals by parameterizing a path and doing f dot dr. So I have the integral from 0 to 1 of this times negative 1. So this is going to be negative 2 times 1 minus t squared plus. Now I'm going to take this thing and multiply by 1, which really just keeps it the same. So I have 1 minus t squared plus 9t squared plus, and then I have that part times 3, 6 times 1 plus t times 3t dt. And so now we need to evaluate that by using the calculator. Now we could do this by hand, but I'm feeling lazy and I don't feel like expanding it. So calculator to the rescue. So I have a calculator that won't stay put. Math 9, 0 to 1. And then I have negative 2, 1 minus t squared plus 1 minus t. Oh, there's so much to type. And I'm being overly dramatic right now because guess what, guys? The fundamental theorem of calculus way is easier. Or not fundamental theorem of calculus. Fundamental theorem of line integrals way is easier. This is just so annoying. 1 plus t 3t dt. 17. Okay, I got 17. Hooray. So I have an answer, but God, that was annoying. It was so much to type. Again, I'm being dramatic. Now, let's do it the other way. Option 2 is use the fundamental theorem of line integrals if you can prove that this thing is conservative. There are 2 ways to prove something is conservative. Option number 1 is determine if the curl of the vector field equals 0, which means determine if this determinant, see what I did there? See if this determinant equals the 0 vector. And this is the one where you have to take each of these partial derivatives and then see if they basically end up canceling out within the terms. Well, here's the thing. If I figure out it's conservative and I figure out the curl equals 0, I'm going to have to find the potential function in order to use the fundamental theorem of line integrals anyways. So I'm not going to do it this way. I'm just going to see if I can find a potential function, because if I can, I'm going to use it. So if I want to find a potential function, that means I need a function where df to x equals 2xy. So if I take that antiderivative with respect to x, I'm going to get x squared y. Cool. I also need a function where df to y equals x squared plus z squared. So if I take that antiderivative with respect to y, I have x squared y plus yz squared. Okay, and then this is that thing where I have one more because it's 3D. So df to z is 2yz. The antiderivative with respect to z would be yz squared. So now I want to see if I can add those together with some overlap here. So my potential function is x squared y plus anything that's a constant with respect to x. Okay, so this would be x squared y plus, all right, now I'm going to look over here and say, well, look, I already had the x squared y. Sorry for the jumpiness. I already have the x squared y. I don't need to write it again. Yz squared is a constant with respect to x. So I'm going to add yz squared. And then if I come over here, I'd be adding yz squared again, which I'm not going to do because I already have it. And this is my potential function. And if you have a vector field that has a potential function and you're finding work done, the integral of f dot dr can be found instead by evaluating your potential function at your ending point minus your starting point. And so that's what we're going to do. We are going to say, well, what was my starting point and ending point? These two. So I'm going to find f of 0, 2, 3 and subtract f of 1, 1, 0 and hopefully get 17. So let's find out. F of 0, 2, 3 using this function f is 0 plus 2 times 9. And f of 1, 1, 0 is going to be 1. 2 times 9 is 18. Take away 1 is 17. Look at that. All right. So when you are calculating work, it is f dot dr. But if you are calculating work in a conservative vector field, then what you can do is you can find the potential function for that vector field by taking antiderivatives and seeing, where they overlap, and then plug in your ending point and your starting point and subtract. So there you go. That is what you need to know.